So now, in the remaining 15 minutes of class, we'll at least get started on normal spaces and tangent spaces. I'm sorry, it took me an hour, right? I thought it was a half hour, but you know, my bad. So I want to talk about, submanifolds of Rn. And so we might call it like a k-fold or something, a k-dimensional subspace, right? So the question is, and here I'm assuming k is less than n, okay? So how do we describe such an object? Like, what even is that? There are two competing viewpoints. And then there's a third viewpoint that's kind of in between. But these are the two really different viewpoints. The one is implicit. The other is, I would say, explicit. Now the explicit you might also call parametric. So implicit, what you do is you have G, a mapping from Rn to R n minus k. All right. And let's say it's a full rank, whatever that means. All right. I'll just put some quotes on it for the time being. All right. Your space M, it's literally just the inverse image of, let's say, some constant vector. In other words, you're looking at g of x equals to that constant. Let me just leave the vector off of that. G of x equal to the constant, I didn't write it right yet. My bad. X in Rn, there we go, such that g of x equals to constant. In other words, your surface, your K surface, your K-dimensional manifold, all right, is the solution set to a system of n minus k equations. The reason you need n minus k is you start with n, all right, and then if this is full rank, then the dimensionality basically is this: n minus k equals to k degrees of freedom. Full rank is essentially the condition that the equations which are implicit in here are independent equations. They have to be independent equations, otherwise you're not really doing the job. All right, so that's what I mean by full rank. Now, so this is the implicit, right? Because if you ask me, give me a description of a point in the space, then I have to tell you, well, it's going to be a point which solves this equation. All right. Now, the explicit is a different viewpoint. I have maybe x, all right, which is a mapping from D, which is a subset, all right, of Rk, and that maps to Rn. And in this context, M is literally the image of D under X. So you want to know what the space looks like on the explicit viewpoint? Well, I can tell you. You just give me a point in the parameter space, and I feed it to my patch, and out pops a point in the space. This is the explicit viewpoint. We use both of these viewpoints in Calculus 3, right? So then the question is, okay, you got these two different viewpoints, then how do we calculate the tangent space to these objects? And what about the perpendicular directions to the tangent space? You know, what even is the right way to look at a tangent space or a normal space in n-dimensional context, right? I mean, in 3 dimensions, tangent planes are nice because, well, you give me one equation in 3 variables, that's a 2-dimensional thing, right? So one equation defines a tangent plane. But if I'm in 4 dimensions and I wanted to describe a tangent plane, I won't need just one equation, I would need 2. If I was going to describe a 2-dimensional tangent plane. Now if I was going to describe a volume, like a 3-dimensional subspace of 4 dimensions, then one equation would do. So these are things we have to kind of grapple with as we're thinking of how do we even describe things. So let me just give you an example here. You should do at least one example today, right? Let's see here. So let's study like x squared plus y squared plus z squared equals to 1, and zw and uzw equals to 10. Right, and so I'm describing some wacky surface, or I don't know how many letters do I got going on here? X, Y, Z, U, and W. So this is a 5-dimensional, right? So these are 2 equations in R5, right? And I'm using, for R5, I'm using Cartesian coordinates, X, Y, Z, UW, right? So that means this is my G, right? So like G of, and I'll use X vector here, is equal to X squared plus Y squared plus Z squared, comma, UZW, all right? And I'm setting that equal to apparently 110. So that's like my C in my general setup over there, okay? So if we pick a particular point in this surface, right? So like maybe you can pick for me what's a particular point in this surface? Let's call this thing, let's say that they define M, all right? So why don't you give me a point P in M. P equals to what is a point in M? Let's make it interesting. My variables go X, Y, Z, U, W, okay? So I'll start us out. 1 for X. How about, once I do that, I'm stuck with 0 for Y and Z. Sorry about that. What do you want to let the U and the W be?
What is G mapping? G is mapping from
Oh, here? G would be a mapping from R5 to R2.
Well, okay.
M is 3-dimensional, so
X
yeah.
is in R. Okay.
Right. Okay, so I made my Z. Oh, this is impossible. I have to fix this. I'm sorry. Once I did that, I can't do this because Z is 0. Oopsie. So let's fix that by making Z like 1/2, and we'll make X like square root of 3/2. Does that work? Then we get 3/4 plus 1/4 is 1. And then I can make U be like what? Like 5 and W be like 4, would that work? That's a pretty interesting point, isn't it? I mean, I think it satisfies equation 1, and I think it satisfies equation 2 because I've got U is 5, 5 times 4 is 20, and then the U and the W are 5 times 4, and then times a half is 10. Okay, okay, great. So then, there's a couple of interesting questions I can ask. I can say find the normal space at P to M, and I can say find the tangent space at P to M. Where by that I mean these are vectors which we think of as based at the point, which either are filling out the normal directions to the space or they're filling out the tangential directions to the space. All right? So obviously the question is, how do you even define the tangential directions to the space? Well, one definition we could give would be, look at all possible curves that go in the manifold, right, that pass through the point P, and look at the collection of all tangent vectors to those curves. Take the union of all said tangent vectors, that gives you a tangent space. Which better be three-dimensional here.
And what is the normal space here?
The space which is perpendicular to this. So I forget what my notation is, but like, let's suppose that VP is the space of all vectors based at P. Then you can see, in fact, that the tangent space to P at M is the direct sum decomposition of the normal space at P to M, where I'm using the it's in fact an orthogonal direct sum, orthogonal with respect to the natural dot product in Rn that's inherited at points at the point P. So here's the cool thing: the normal, like this, in this viewpoint, this guy is a bear. This is hard. It's hard to calculate from our current viewpoint. This right on the other hand, easy. The reason it's easy is that, well, let me just prove it to you. Check it out. If we had G of gamma of t, right, equals to C. In other words, I'm supposing we have a curve that is on our manifold. It's on our k-dimensional space, right? That means that G1 of gamma of t and G2 of gamma of t, they're both actually give me what? Well, in this particular example, 1 and 10, you know? So if I differentiate these, right? If I differentiate this with respect to time, the chain rule tells me that the gradient of G1 dotted with d gamma dt is equal to 0, and the gradient of G2 dotted with d gamma dt is equal to 0. But this is for arbitrary tangent vectors. Therefore, these must be normal. The gradient of the level function, the gradient of the component level functions are giving you normal vector fields. So like for this one, the gradient of G1 looks like 2x, 2y, 2z. There is no u and w dependence here, so I just do 0, 0. The gradient of G2, on the other hand, well, G2 has no x component, so the x partial derivative is 0. The order of the partial derivatives is informed right here. So the gradient means partial x, comma, partial y, comma, partial z, comma, partial u, comma, partial w in this 5-dimensional space. So there's no x, 0. There's no y, 0. There's a z, so that's going to be uw. And then the partial derivative of that with respect to u, zw, right? And the partial derivative is uz. So these actually define a pair of normal fields to the manifold, and then we can specialize to the point that we constructed, right? So the particular point we've got, you know, del G1 at the point P, what's that? Del G2, goodness gracious, at the point B. So yeah, what'd you got? Oh, square root of 3, okay.
0, 1, 0, 0.
All right, cool. And these?
And then 0, 0. Trying to say what you the last one. Yeah.
20? Is it 20?
2 square root of 3.
I meant UW?
Oh, I'm sorry. 20.
Yeah, 20. Then ZW, which is what? Oh, you said 2? Yep, very good. Okay. So the span of these two guys is the normal space at P in this 5-dimensional space.
The span of those two?
Yeah, the span of these two. Like these two, the normal space is 2-dimensional.
Yeah. Okay.
Because the space, the subspace we're looking at is 3-dimensional. So the total dimension has to be 3 plus 2 is 5 in our context. And yeah, the span of these two fills out the normal space. Now, so what are the vectors in the tangent space? How do you find those?
Are those the partial?
Well, yeah, so from this perspective, we have no real choice but to do linear algebra. See, the problem you face is to find 3 perpendicular vectors to a given pair. How do you do that? How do you find perpendicular vectors to a given pair?
To a given pair.
Yeah, how do I find vectors which are perpendicular to these two?
The cross product then.
Ooh, 5-dimensional cross product. Very ambitious.
In this case,
So one way you can do it, we have a theorem that if you have a set, which is a subset of like Rn, right? And you want to find the perp to that, it is the null space of the matrix of S transpose. So you can straight up calculate, basically you just need to calculate what's the null space of the matrix root 3, 0, 1, 0, 0, 0, 0, 20, 2, 5 halves. Those are column vectors, I transpose them. So I can tell you some things in here, like for instance, here's an easy one, right? That's in there because, see anything else?
I mean the 0.
Well, that's true, but we're looking for a basis.
Okay.
0 is in there, that's good, yeah. How about this? What if I do 0, 0, 0,
And 1, 0.
and well, 1, 0 would still dot product. So I need to play the flip a negative game.
Okay.
So like if I do minus 5 halves, 2, I think that would do it because when I take the dot product,
Yeah.
when I take the dot product of the first one I get 0 because it's zeros and zeros. And the second one I get minus 5 plus 5, 0, great. But we're still Guessing has got us this far. Now, of course, you can straight up do the row reduction. Actually, it's easier to do the row reduction than my stupid guessing. Like, good grief, like this is like pretty much already done, right? Like, do you know the calculation I'm talking about?
Yeah.
I mean, this tells me, man, I really just need a little bit. So this one here, I think we don't need this comment up here anymore. So I have on the one hand, the square root of 3 x1 equals to minus x3, and then I have 20 x3 equal to minus 2 x4 minus 5 halves x5. Now I really should clean up. I really should subtract that out before I did that. My bad. Like I need to like clear that out for best results here. I'm not doing my row reduction like I should. So this gives me what? Root 3, 0, 0. I'm going to subtract 1/20th of the second row, so that gives me negative what? 1 over what?
10.
1 over 10? Okay. And 1/20th of that, 5 over 40? Oh, you say 1/8?
Sorry.
Yeah, minus 1/8, I think.
Yeah, 1.
I mean, we'll find out soon enough if we're right or not, because it'll be glaringly obvious when we look at the equations here in a second. Now, who cares if you normalize these? Doesn't matter, right? And this tells me that, like, x1 is equal to 1/10 x4 minus 1/8 x5. And this tells me that x3 is equal to minus 2 x4 minus 5 halves x5. And so then,
Should we have a positive sign in front of the 180?
I should, thank you, that's going to hurt us in just a second. So then my generic vector in the null space looks like what? 1/10 x4 plus 1/8 x5, right? x2 is free. x3 is minus 2 x4 minus 5 halves x5. And then I've got x4, of course, is x4, and x5 is over here. And then if I just peel out my x4, I've got 1/10, 0, minus 2, 1, 0, plus x5 times 1/8, 0, minus 5 halves, 0, 1, and then plus x2 times 0, 1, 0, 0, 0. And of course, we guessed this one already. But you can check that the dot product of this would. That's no bueno. I lost that root 3. Oh man, that matters. That stupid root 3, it's still here. Son of a gun. That means I have to divide by root 3. Root 3. This is root 3 here. Root 3. It just affects these though, right? Yeah. So that puts a root 3 here, right? Where else? Here? So
The same with 20. I mean, because 20x30 equals negative 2x4 minus 5.
yes, and the same with 20. Man, I'm trying to skip a step. Let's see what gets me. So let's see here. That's going to be the 3. So I just divide by 20. That becomes a 40. Here, this one, right? There. All right, if I finally did it, if I did it right, then when we take this and put it against that, yeah, see the root 3's cancel, we get 1/10, minus 1/10, and then, yeah, this dot that is 0. This dot that is minus 2 plus 2, which is also 0. Yes, this is perpendicular to both normal vectors. And this one, the root 3's cancel, and you get 1/8 minus 5/40, 0. And when I dot product with that, I get, math. Ah, 100 over 40, minus 100 over 40, plus 5/2, also known as 0. Great. Dot product 0. And finally, this is obviously dot product to 0. So there you go. And by construction, these are linearly independent because they're the basis for the null space. And there you have it. That's your tangent space. That's what the calculation looks like if we're describing the surface implicitly. However, if we were instead describing it parametrically, the tables turn. It then becomes easy to find the tangent space because it's just partial differentiation. And then to find the normal space, we got to do this stuff again. Because unfortunately, in n dimensions, you don't have a cross product. So you have to rely on the magic of the orthogonal complement theory. Now, there is actually something else that could be done here. You could actually take these two vectors, and you could also supplement them with those two vectors, and you could put them in a 5x5 matrix and make the top row E1, E2, E3, E4, E5, and that formal determinant will produce a vector which is perpendicular to all four of the ones you're given, and by logical consequence, it must be the missing third vector. It is possible. There is a analog of the cross product, but it's not a product. It takes four vectors in, and it outputs a fifth orthogonal one. This is not widely known. Well, I don't know how wide. My brother wrote a paper that we thought about. I'm not an author on that paper, but it's part of a conversation that was ongoing for a while. Anyway, I think I better zoom in on that calculation. Otherwise, I'm going to regret it. Oh man, that's tiny. Well. Yep. So anyway, we'll do more of this next time. I love this calculation.